All right, so one of the questions that I had this morning was, what's the best way to learn statics in the shortest amount of time? That's a good question. All about efficiency there. My answer to it's kind of informative to a little bit of how I approach this class, and that is that this book, all your textbooks, if you look in the beginning of them, or the end typically, there is a list of people who they thank for reviewing the book. And it's a lot of people. And my, here you can see under acknowledgments here in the book, there's a list of all these different people who are professors that teach this subject year in and year out, that have reviewed this book and said, hey, here's some suggestions for how you might teach it better. And that includes the order things are presented in, how they're presented, what examples are there. And I believe it would take a lot of hubris for me to say, I know better than them, so I'm going to do it differently. Okay, so I think these people probably know more about teaching than I do. And so I follow a lot of what they have done. And so we are going to march right on through this book. I think we go through 8 chapters of the book, and if you're ever lost, go ahead and take a look at the book. And I think that the book is actually, if you can learn from reading a book, that's wonderful. I have no problem being useless to you, right? So read the book. And I think when I lecture, I'm going to go down all sorts of odd rabbit trails, which I find enjoyable, and I hope you can enjoy them a little bit, so that it's not just like reading a book. But if you can learn from just reading the book, more power to you. It will be the densest, most direct way to get the information. And so totally recommend reading the book. And it also kind of is a good guide for where we're going in the class. So statics is really part of what we call engineering mechanics. And this is really fun because I assume you all want to become engineers, and that's why you're taking this. And this is really the first time that you're going to be taking a class that is really engineering and really meat and potatoes engineering. So last year we had kind of the intro sequence, graphics, and intro to programming, and just intro to engineering. But this is the first really computational, you're going to be doing engineering, right? So in physics, you deal with forces and things like that, and that's what we do in engineering mechanics too. So engineering mechanics is really the study of forces and their effects. Okay? And this is sort of similar to what you do in physics. The first term of physics, you're going to spend a lot of time looking at forces. But in physics, all you're looking at is really the science behind them. And in engineering, that's what I like about engineering, is that it's very applied. So we're taking that science that physicists and chemists and materials folks come up with, all that hard science they do, we take and then we turn it into stuff, right? Engineering is about taking science and applying it to our world to make it better. So a long time ago, somebody invented the wheel because they were tired of dragging things, I guess. I don't know why they invented the wheel. And then someone looks at that and says, hey, let's make a bicycle. I'm tired of walking places on my feet. And from the bicycle comes the car, right? And we get planes and all these different things that really, the goal is to make our life simpler. That's my kind of mantra, that a good engineer is a highly motivated, lazy person, right? You are looking for the way to make things easier for everyone. Alleviate drudgery, as one of my professors used to say. So we're definitely applied. We're looking at forces and their effects. And really, this then splits in half. Does anyone remember any of Newton's laws? An object in motion tends to stay in motion unless acted upon by a force in balance, right? Yeah?
Every action has an opposite and equal reaction.
Every action has an opposite and equal reaction, yep. And that object in motion one, I think, is where we really get this F equals ma, right? Force is equal to mass times acceleration, right? So we got our force. Force mass and acceleration. So when I say mass, what do you think of? Chase?
Kilograms or like
Kilograms,
the
okay.
weight of something.
The weight of something. All right, you did air quotes
Yeah.
around weight. Why'd you do air quotes around weight?
Because weight isn't actually a constant thing for an object. Mass is, but an object does not have a constant weight. It'll have a different weight on a different planet.
Sure, so weight isn't constant. It changes due to the gravitational pull on it, right? But this is something that I think is a difficult concept to grasp because we are so used to living on Earth and we're so used to experiencing mass as weight, but they are different. And I think the best way to think about this is really to look at F equals ma. So weight is a force. It is the force of gravity on me, on this table, on a computer, on anything in Earth's kind of gravitational field. The weight of that object is its mass times the acceleration of gravity, right? So for instance, you are seeing Summer Andy. I will develop my winter coat, and by next summer you'll be seeing Winter Andy. I lose 10 pounds during the summer probably, and then I gain it back between Thanksgiving and Christmas. So Summer Andy weighs just a little bit over 220 pounds, okay, or 100 kilograms. But wait, we're going to get confused here because kilograms is mass, right? Isn't kilograms mass? But is pounds force or is it mass? It's force, but it can be mass. Super confusing. We're going to talk about this for a minute. So I'm going to tell you that my 220 pounds is a force, and that's equal to my mass times the acceleration of gravity, which in the U.S. system, U.S. customary, is 32.2 feet per second squared. Okay? So we could figure out what my mass is. My mass would be 220 pounds divided by 32.2. And I should say that I don't bring a calculator to class usually on purpose because my expectation is that you bring a calculator to class and will do math for me. So 220 divided by 32.2. Yeah, you can do it on your phone.
So how come you use the feet per second squared and not the meters? Like what, for
Yeah.
unit wise, why?
Yeah. We'll get there in just a second. So what is it? 6.83. Anyone know the unit? Giving you a hint. Giving you half of it. Slugs. Not like the, beady-eyed little invertebrate. Not that type of slug, right? This actually stands for sluggish. Because I want you to start thinking of mass as resistance to acceleration. Okay? So when 220 pounds acts on my mass of 6.83 slugs, that's the weight that my feet feel sucking down onto the surface of whatever I'm walking on. Okay? Now, let's say that you shoot me with a rubber band. Please don't. But let's say you did. And that rubber band imparts to me a 2-pound force. Right? Does that seem about right? Think a rubber band could hit you with 2 pounds of force? I have no idea. Maybe it's 1 pound of force. Let's make it 1 pound. Not much is the answer. Okay? So according to Newton's first or second law, I think this is the second law, F equals ma. So that 2 pounds of force acting on my sluggish mass of 6.83 slugs will result in some acceleration. Could you figure out what the acceleration is? It'd be 1 divided by 6.83. Excuse me?
0.146.
0.146 feet per second squared. Okay? Now let's say instead of shooting me with the rubber band, you shoot a paper clip. Okay? It still imparts 1 pound of force. The paper clip, though, has a mass of, gosh, I bet I weigh 1,000 paper clips. Don't you think? I bet I weigh 10,000 paper clips.
0.306.
So 10,000 paper clips would be 1/10,000th of this. Can you divide 6.83 by 10,000? I think it's going to be 0.0006. Right? Is that right? 6.83 divided by 10,000? 3 zeros and then 6?
Yeah.
Okay? Now figure out what the acceleration is. I'm guessing it's, what, 14,600?
Yeah, or 1464.
Oh, 1,464
Yeah.
feet per second squared. I do this to point out to you, look, the force doesn't have as much effect as the mass that it's acting on, right? Or I guess it has a proportional effect. But mass, if you hit me with 1 pound of force, pretty low acceleration. If you hit a paper clip with 1 pound of force, pretty high acceleration. Because mass is a resistance to acceleration. Okay? We aren't going to really need to worry about this a ton in this class, but I want you to start now thinking about mass as resistance to acceleration. Okay? So it's how hard you're trying not to accelerate. Okay? So let's get back to engineering mechanics. We're talking about forces. That's engineering mechanics. And so it's the forces and the effects of forces on bodies. And we split that into places where F equals ma. This is dynamics. So that's things are accelerating. And where we say the sum of the forces is equal to 0. Oh my gosh, look at that summation sign. I can't do summation signs in the fall. It takes me until spring to get my summation signs back. Okay. So this is dynamics. Statics is the sum of the forces equals 0, which is a really good way to get introduced to forces and their effects in engineering mechanics. So when you're driving down the freeway at 60 miles an hour, 55, we're in Oregon. If you're driving at 55 down 84, are you in static equilibrium? Which of these cases? Are we in statics or are we in dynamics? Okay, so I've got to vote for dynamics. Dynamics? Okay.
I think it just depends on what.
So it does depend, and it depends on whether you're going around a curve or not. Because if I'm traveling in a straight line, what's my acceleration at a constant velocity? What's my acceleration? It's 0, right? So if I'm traveling at a constant velocity, I have 0 acceleration, which puts me actually in statics. It's tempting because we're used to saying something that's dynamic is moving, right? And something that's static is at rest. But in statics and dynamics in engineering, statics means not accelerating. Dynamics means accelerating. Okay? So this class, we're concerned about things that may or may not be at rest, but are certainly not accelerating. Okay? That's going to be the key in this class, is that everywhere we go, the sum of the forces is going to be 0. Okay? Now, as we do this, we need to talk a little bit about how we talk, right? So there are some base concepts that we kind of need to cover. And it's how we measure stuff. So in engineering, there are 3 base measurements. Can anyone guess what one of them is? Chase.
Kilograms? Or like base measurements, do you mean like mass?
I don't mean, yeah, I mean more concepts than units themselves. Okay, mass. All right, so we're going to say base measurements. Measurement concepts. One is mass, right? And we've kind of already defined that as what? Nailed it. Resistance to acceleration. Okay. What do you think another base measurement concept is? I'm sorry?
Volume?
Okay, so volume is derived from it. What is a volume? Conceptually.
Mass over density?
No.
Mass. Something like that.
What's units of volume? Let's start there.
Liters?
Okay, liters is a unit of volume. How else do we do it? Centimeters cubed, right? So what's the measurement concept of a centimeter? Length. Yeah. So another one is length. And see how we can get volume from length, right? Liters is a little bit different, but it's actually, I believe, is there 100 cc's in a liter? I can't remember, but it's cubic centimeters.
1 milliliter is a cubic centimeter.
1 milliliter. So there's 1,000
Yeah.
cc's in a liter, and that's a cubic centimeter.
Oh, okay.
Okay. So length, this is some distance measurement, we'll say. Okay. And what's the third one?
Direction.
No, because density, right, we think of as a mass per volume, right? So that's these two put together. Direction, that's, no, not it.
Angle.
No.
Velocity.
What do we need for velocity? What is velocity? But like, what are the units? We need time, right? Because it's a length per time. So really, these, gosh, how do you define time? The concept of time. This isn't philosophy. I'm going to leave that one just as an arrow. You get the idea of time. So mass, length, and time are kind of our three, what we call base units. Now, the reason that there's some conflict between the SI system and the US customary system is because rather than having mass be a base unit in the US system, we have force as a base unit. In the SI system, force is derived. So the unit of force in SI, so now let's look at units. So in the SI system, mass, I'll write the concepts here, mass, length, time, and force. Okay, so in the SI system, the unit of mass is the gram, or in engineering, we actually take the kilogram as our most common base unit, right? And that's kg. In the US system, it's the slug. Okay. For length, we have meters. In the US customary, depends on what you're doing. It's either inches or feet. And we'll say feet probably for now. That's kind of one of the annoying things, right? We have inches, which are like 12 of those in a foot, because that makes sense. And then there's 3 of those feet in a yard. Again, not sure why. And then there's 1,760 yards in a mile, or 5,280 feet. Come on, guys, this is weird. And it has something to do with the distance from Athens to some mountain or something, and blah, right? Time. Well, we use, let's say, seconds for both of those, okay? And in force, in the SI system, that's a Newton, which a Newton is 1 kilogram accelerated at 1 meter per second squared. So it's a kilogram meter per second squared. And I'm getting that directly from F equals ma. So in the SI system, we derived our force value, the Newton, so F equals ma, as being 1 Newton is equal to 1 kilogram going at 1, or accelerating at 1 meter per second squared. And so I get a kilogram meter per second squared for the units. Okay. And in the US customary system, we have the pound. Okay. Now, in the customary system, our standard, I forget how they came up with this. It was probably like, I don't know, if 2 pigeons float or something. Somehow they came up with a standard of what 1 empirical pound was. Right? And then they had to go back when they realized, actually we need to figure out what mass is and develop the concept of a slug. And so how they did that is that they had their standard of 1 pound accelerating at 32.2 feet per second. So 1 slug, here's what I know. 1 slug, if it's moving at 32.2 feet per second squared, that's the acceleration of gravity on Earth, gives you 32.2 pounds. This system sucks, right? So we really like the SI system. And Zach, you asked, how do I know whether I'm using feet or whatnot? If there are these units in the problem, you have to stay with those units, right? So if the problem says something's 10 feet away, then know you're going to want to use this, which means the acceleration of gravity is 32.2 feet per second squared. Whereas if the problem has units like this, you know that you want to use the SI system where the acceleration of gravity is 9.81 meters per second squared.
It was because originally I didn't know a slug was a unit.
Oh, yeah. Isn't that crazy? Okay. I kind of like it because its name more communicates what mass is. It's sluggish. It's resisting acceleration. Whereas kilogram we just take for granted as a weight because we're used to interpreting kilograms on the surface of the Earth. Okay? All right, let's talk a little bit about numbers. So we're going to use engineering notation. Anybody know what engineering notation looks like? I remember having to do this in like some silly physical sciences class where you had do you remember scientific notation? What's scientific notation say? Yeah?
Instead of doing like to the 10th power, use E.
Oh, okay, so if I have 3,678, how do I put that into scientific notation?
40.678 e to the third, I think.
Okay, and I would actually say that, oh gosh, like this?
Yeah.
So I think scientific notation, you actually can use it, you would just say times 10 to the third. That's how I'm used to doing scientific notation. But you turn the number into a number that's between 1 and 10, right? And then you use the times 10 to say what it is. So like, how about, or earlier I had, what was it, 0.00683. That would become 6.83 times 10 to the minus 4, right? Everybody familiar with this? So in engineering notation, rather than making it be a number between 1 and 10, we make it be a number between 1 and 1 and 999. Okay, so 3,678 would become 3.678 times 10 to the third. And 0.00683 would become 683 times 10 to the minus 6. Okay.
So with that, why wouldn't you just?
Couldn't you just stick with regular scientific notation?
Yes, you can absolutely skip the scientific notation. Yeah, we won't be doing any scientific notation. I was just saying, since people are familiar with this, how are we doing that? And the trick here is, because we're doing it between 1 and 999, all of these are going to be a power of 3. Why do we do that? Well, let me give you a few more numbers to practice on. So let's do 15,782. What would that be?
15.782 times 10 to the third.
Exactly. How about 0.7?
700 times 10 to the third, or negative third.
Right? Because when I have 10 to the negative 3, I'd take the decimal place and go 1, 2, 3, and I'd have 0.7. Okay? Why do we do this? Because, isn't this great? I found a box of dot matrix paper in the corner, so I'm using it. Could probably sell it for a mint on eBay. Okay? We do that because we use prefixes in engineering all the time. We start at giga. It's a capital G, and it means times 10 to the 9th. So it's a billion. Then we have mega. It's a capital M. It's times 10 to the 6th. We have kila, which is just a lowercase k, and it's times 10 to the 3rd. We've got nothing for kind of 0. We have milli, little m, for 10 to the minus 3. We have, anybody know what's next? Micro, which is the lowercase mu, 10 to the minus 6. Nano, that's lowercase n, 10 to the minus 9.
No, it's way smaller.
Hmm?
Penta or something? Or
Close. I think it's pico,
Oh.
right? I think it's pico. Assuming it's a p, I don't really know actually. 10 to the minus 12. And I think femto
And then it goes down to.
is 10 to the minus 15. I think. I actually have no idea. Anybody know where an angstrom is?
Angstrom is the smallest one that we can.
It's 10 to the minus 10. It's angstroms. Okay? So, well, I'm not sure about these. We don't really care about them. We don't deal in that space. Okay? But so now, if I tell you I have 679 newtons, that's fine. If I say I have 679,432 newtons, in engineering we'd say, no, you don't. You have 679.432 kilonewtons. Okay? So I expect in your homework all answers to have only 3 numbers in them. Right? Anybody ever taken a class that involved significant digits? Okay? They were doing it wrong for engineering. All right? Because the rule in engineering is there's always 3 significant digits. And that's because it gives us 1% accuracy, which we assume that whatever measuring device you're using, you can get 1% accuracy with. Okay? This is a pretty good assumption because if you're using a tape measure, what's the smallest measurement on a tape measure? 1/16 of an inch. 1/16 of an inch, which is equal to 0.0625 inches. Okay? Pretty close to, in terms of a foot, that's a lot better than 1%. Okay? If you're using a scale, when I get on the scale at home, do you think it can measure my weight plus or minus a couple pounds? Probably, right? That's 1%. Okay? when I use a stopwatch to measure how fast I'm going, do you think I could, is a speedometer in my car good to plus or minus 1%? Well, doesn't have very good graduations in there, like little specks. But if I got out a stopwatch, could I figure out my velocity within 1%? I think I could. Okay. So in engineering, we're assuming that all data is given with plus or minus a percent. So we always use 3 significant digits. That makes it awesome to use this system. Because now instead of having 679.432 newtons, I have 679 kilonewtons. Okay? Does that make sense? So I just rounded that, right? See some deer out there in the headlights. You all right? It's afternoon.
So like in our final answer, when we're like reporting an answer or something,
Yep.
the top one, because that's the 3, that's within 1%.
Yep, that would be your boxed answer right there. Yep. I am not a stickler on this stuff, but this is good. You carry this all the way through doing the calculations, but then round it at the end to get your answer.
And it's not like something where you always have to round down.
Ah, good question. So Zach wants to know what my rounding rule is. How do you guys round the number 5? Up or down? Okay, that's because you're not communists. No, I don't know. There's this great, I love the book. It's so funny. Here, they talk about rounding numbers, and this is the only book I've ever seen that does this. Okay, down here, as a general rule, if the digit preceding the 5 is an even number, then the digit is not rounded up. If the digit preceding the 5 is an odd number, then it is rounded up. For example, 75.25 rounded off to 3 significant digits becomes 75.2. Whereas 1.1275 becomes 0.128 because 7 is odd, so you round up. That makes no sense. I believe they're doing it to statistically average it. I think it's dumb. So we don't do that. If it's 5, round up. But I enjoyed that little tidbit. Okay?
This might not be relevant, but can we round at the very end of all of our calculations?
Yes.
Okay.
Yep, rounded the.
Use more digits.
Yep, you use the digits all the way through and round at the very end. Okay? So we've got common language of numbers. Let's try a common, there's a couple idealizations or assumptions that I think are important to review. The first one is the idea of a particle. Okay? So I could take a school bus. It's going to take me a while. Got to draw all the windows. Okay, there's my school bus. What forces do you think are acting on this school bus?
Gravity,
Yeah, gravity is. Where do you think gravity acts on the school bus?
top of it, I think, or all of it?
Sure, yeah. So there's gravity on the rear bumper pulling it down. There's gravity on the front bumper pulling it down. There's gravity on every window here pulling them down. Lots of gravity, right? Where might we draw this instead of like having all those little pieces?
Below it, just like directly below.
So typically we'd put it someplace we'd say, here's what we call the CG, right? The center of gravity or the center of mass. And we just put one big arrow coming down, right? And we'd say that's the force of gravity. Where else is there force acting on this?
Front of it,
No.
air resistance.
Okay, yeah, if we're moving, we could say that there's some air resistance, sure.
Maybe below it, acting up.
Yeah, Zach says there's some acting up at the back wheels. Is that what you're talking about?
Yeah.
Is there any on the front wheels?
Yeah.
Yeah. So these we would call normal forces, right? This is, we'll call this F sub D, force of drag. How's the bus moving?
Oh, you have friction.
Yeah, so we've got friction that's actually pushing it forward. Don't worry about that right now, but it's true. Friction's pushing it. Okay, that gets pretty complicated. We will get to doing problems like this. A particle, though, says, instead, let's treat the bus as a particle. And all the forces act through this point in space. And a particle has mass, but no size. Right? So a particle has a resistance to acceleration. That's what mass is. But it has no size. So here we can just say we've got g acting down, or I guess I'll do little g. That's probably better. And then we have the normal force of those tires acting up, right? And then we'd have the force of drag acting this way and the force of friction acting that way. And they all act coincident on one point. So a particle, we're saying we're reducing the effects of this thing having size. We're saying that the fact that it has size doesn't play a role in the problem, and we just call it a particle. And this is how we will start. So we're going to start for the first several chapters looking at particle statics, and then we'll switch and go to rigid body statics. Okay? Now, rigid body, that's another assumption as well. So the best way to think about this assumption is to think about a beam, which we'll be looking at lots of beams this term. Okay? And let's say I park my giant keister out on this thing, right? So we know now that Andy has 220 pounds of force acting down on him, so that means the beam has 220 pounds on it. Is that beam going to deflect?
Maybe noticeably to our eye now.
Any other thoughts?
What's it made out of?
What's it made out of? Okay, that's reasonable. Let's say it's a 2 foot by 4 foot chunk of steel, and it's 8 feet long. Okay, you're not going to be able to measure it. It's not going to deflect the 1% threshold that we're talking about, is it? Is it actually going to deflect? Yes. Right? If we had some laser microscope and we looked at that thing, when I stand on it, I cause it to deflect. You're all deflecting the tables right now. You're deflecting the chairs. You're actually deflecting the concrete too, right? You will learn in engineering, anytime you put a force on something, you cause it to change shape. It's just whether you can see it or not. Okay? So everything, every time we touch it, so like when I squeeze this cup, we can see I'm deforming it. And that's what we're used to thinking about, is a visual deformation that I can see and evaluate. That's not what deformation, I mean, that is a deformation, but that doesn't mean that when I push on this table, I'm not deforming it also. I am, you just can't see it. Okay? So in a rigid body, though, the rigid body assumption says that actually this is a dirty, rotten lie, but we're going to say things don't change shape. Why is this okay? Well, let's say it's actually just a 2x4 on edge that I'm standing on. It deflects, but not a whole lot, right? So it's going to deflect just a teensy-weensy little bit. But does that change my calculations significantly? It doesn't. And so the rigid body assumption greatly simplifies our calculations and is a legitimate assumption for almost all cases. Okay. The last assumption that we'll talk about is the concentrated force. So back to this, when I stand on my beam, my shoes, I probably end up taking up about a square foot. Right? So there's actually some distributed load across that whole thing. But instead, we often would say, nope, Andy is standing 4 feet from the end of the beam, and there's just one point at which that load is applied, okay? It doesn't cause any funky deformations, which actually if you had a point load it would, but we're just saying a concentrated force can act exactly at 4 feet. So it's acting essentially over no area, okay? And this assumption is good as long as the area over which we're applying the force is very small. So we'll kind of get a feel for these. I realize these kind of are a little vague and ethereal at the moment because we haven't done any problems, but once we start doing problems, these are the 3 assumptions we'll be making. Rigid body, particle, and concentrated forces. All right? So we have covered today all of chapter 1. All right? I'd like to point out in your book, if you look in just kind of as a matter of format here, so this is section 1.6, okay, so it talks about the general procedure for analysis, and it includes in blue here these important points. So these are things that you should know going forward. And as we look later in chapters, it will give you a procedure for analysis. And this is where it tells you step by step what you should do. So here you need to use the parallelogram law. So in order to do that, it tells you exactly what to do. So if you're solving problems and are lost on how to get started, look for these green areas at the ends of the section preceding the problem you're working on. It's this that I'm going to be doing for you in class. We'll work a ton of examples come Wednesday, or in Wednesday's lecture, I guess. So you'll observe me working examples. But if on your own you're looking for how do I address a problem, look to these green sections in the book. That's really what they're there for. Okay? That's all the content I want to cover today. It's all the content I covered in today's morning lecture. Do you have any questions for me about what we covered or expectations? Yeah.
What time do you usually get the lectures posted?
Yeah, so that's a great question. What time do I get them posted? I'm going to see here, it usually takes a couple hours for it to format and upload. And so it'll be, if you don't see them, I'd say by 3 o'clock, feel free to email me and say, hey, something went wrong, it's not up there, because that has been known to happen. Okay, so they should be there by 3 in the afternoon, day of the lecture. Okay. We will have a quiz on Monday, and there is homework due on Monday. I think we should get to all of the stuff we need to have the homework done. If not, I will let you know. Next Monday, I am going to be gone Monday and Tuesday next week. Would you guys be available on Wednesday next week only? The same bat time, same bat channel. So at noon on Wednesday, would that mess with anyone's schedule? Think that'll work? It won't work for you? Okay. It doesn't work for you? It does. Okay. All right. So it's Rebecca, right? Okay. So let's talk after class. We'll come up with a plan. For everyone else, let's plan on meeting next Wednesday so that we can have, I don't want to go 2 weeks without having face-to-face, how's it going, what issues are coming up. If something comes up and Wednesday doesn't work for you, please email me and we can come up with an alternative time to meet. But and I will continue to be posting videos, but we will plan on, so our quiz, I will plan on having on Wednesday, and the homework for you guys will be due on Wednesday this week only, because I'm going to be gone Monday and Tuesday.
You just do the stuff in the syllabus?
So the stuff in the syllabus is just practice. I'm not going to collect that. So there is a homework problem. I'll show it to you here. There is a homework problem that is, I'm going to stop this.